Hey my fellow intellectuals, welcome back to my channel. What I'd like to do today is I'd like to go over this simple harmonic motion problem that I was demonstrating to my class that I TA for this summer. And I actually got this problem wrong the first time I tried to solve it. And I kind of want to go through the process of how I got it wrong, sort of the thinking that went into why I was wrong, and then how I self-corrected and ended up getting the right answer. So why don't we just get right into it? So, like I said before, this is a simple harmonic motion problem. It involves a mass of mass m, and it's attached to a spring that's attached to a wall. And this is a frictionless surface that it's on, so there's no friction whatsoever. There's no damping or drag forces, so there's no dissipative forces whatsoever. And part of the problem had us solving its position equation, x of t, as a function of time. And we ended up getting this equation for the position. And so this gives us the position at any time of the block along its trajectory. And because the amplitude is 0.25 meters, it means it will spend its time oscillating between these 2 points. And so that's the basic setup. The problem that I was trying to show my class was, when are the first 3 times, t1, t2, and t3, that the position is equal to negative 0.20 meters? So what are the first 3 times that it appears at negative 0.20 meters? The initial approach I had was to calculate the very first time, t1, that it's at negative 0.20 meters, and then I was just going to add the period of oscillation once and then twice to get the second and third times respectively. Now the period of oscillation just tells you essentially the amount of time it takes. So if you have a function like this, it represents the time between 2 peaks or 2 troughs, effectively, which I didn't actually draw a full trough here, and that's probably not well drawn. And that's very important to keep in mind, because this is why I got the problem wrong. So keep that in mind. Keep this sort of picture in mind, that the period is just how much time it takes for this to happen. And I'm going to show you how you can relate the period to this quantity right here, which is known as the angular frequency. And so what I did effectively was I did some algebra. I essentially solved for t1 because I have everything I need essentially. I know that the position that I'm solving for is negative 0.20 meters, and I just plug in, not plug in, but I just write down the equation that I start with here, the position equation. And I'm just trying to solve for t1 here. So I just do a bunch of algebra here, solving for t1. And you can see that I'm using a bunch of units just to keep the units straight in my mind, so I know what mode my calculator should be in. And so I effectively am trying to isolate t1 here. And so with this algebraic process, I found that t1 is equal to 0.22 seconds. And the period of oscillation is related to this quantity, 10 radians per second, in this problem via this equation right here, 2 pi over omega, where omega is the angular frequency. And so if you solve for the period, you'll find that it is equal to 0.63 seconds, just plugging in the known value for omega here. And so my approach was to simply just add 0.63 seconds to get 0.85 seconds for the second time, and then add 2 times the period to get 1.48 seconds. Now, I'll tell you why this is wrong, and this goes back to this drawing I have here. The period represents how much time in between maxima and minima of the function. And the position, negative 0.20 meters, is not a minima or a maxima. And hence, if you actually look at a plot of x of t, so I actually plotted this out in Python, and I plotted out x as a function of t, and you can see here that t1 I got right, it is 0.22 seconds, but t2 is apparently 0.35 seconds, and t3 is 0.85 seconds. So in fact, the second time I derived here was actually the third time on this plot. And the reason I got it wrong is because I forgot to realize that this block, if we want to think about it in a physical way, is going to go down, right? Starts going down, reaches negative 0.20, reaches its maximum of negative 0.25, and then has to go back through negative 0.20 on its way back up. So effectively, on this drawing here, it essentially goes to negative 0.20, let's say negative 0.20 is right here, reaches negative 0.25, and then it has to go back through negative 0.20 and that's within one period. So effectively, this block reaches this point more than one time within a period because it's not at its minima or its maxima, which is why I had that problem wrong. So effectively, I solved for T1 right here, and this is effectively T3 based on what I found in my code. So I did my code, I wrote my code and I got the answer, but I wanted to figure out, how do I get T2 actually? How do I derive 0.35 seconds? So now this is how I solved that. So my new approach was to take a step back and think about trigonometry. What is the angle, right? What is this angle in this argument for the cosine at t is equal to t1? Well, if you go through the process of plugging what t1 is, it's 0.22 seconds, and then you figure out that this is 2.48 radians. The cosine of that is negative 0.79. And you convert this to degrees, you find that this is 142.1 degrees. So this is the angle. This is in quadrant 2 on the unit circle, if we remember our unit circle, which I actually will have drawn a few down below, so we'll get to that. But the new question in my mind was, when is the next time, t2, when cosine of 10 radians per second times t plus 0.28 radians is equal to negative 0.79, negative 0.79. Because that's what the value was at t1, right? So this was the new question. When is the next time cosine returns to this value of negative 0.79? So if we recall the unit circle, and I've drawn the 4 quadrants right here, 2.48 radians is something around here. I'm not being that precise. And I was trying to remember, okay, when is the next time cosine is going to attain that value of negative 0.79? I want to say there's units, but there's no units on it. It's a dimensionless quantity. But, I remembered that, since cosine is an even function, that means cosine of x is equal to cosine of negative x, right? So cosine of 2.48 radians is equal to cosine of negative 2.48 radians. Or another way to think about this is cosine of essentially 0 radians plus 2.48 radians, which is this angle right here, is equal to 2 pi radians minus 2.48 radians. So effectively, you can think of 0 and 2 pi being right here, and negative 2.48 radians would just be essentially subtracting or just going, 2.48 radians in the negative direction. And so if you go ahead and solve for what the degree angle is of what 2 pi minus 2.48 radians is, you'll get that it's about 218 degrees, or 217.9 degrees. That's in quadrant 3. And so that's what I've drawn right here. Remember that cosine is negative in quadrants 2 and quadrant 3 because of that acronym I always never seem to remember. It's all students take calc. And all of these letters in the acronym tells you which trigonometric functions are positive, right? So all the trigonometric functions, sine, cosine, tangent, are positive. Quadrant 1, sine is positive in quadrant 2, tangent's positive in quadrant 3, cosine's positive in quadrant 4. And so cosine is going to be negative in quadrants 2 and 3. And we found, based on this analysis right here, what those two angles where cosine attains the value of negative 0.79 is, right? So again, this was to solve a simple harmonic motion problem, but I'm really just reformulating it in terms of a mathematical problem here. And so if we figure out that indeed that at cosine of 2 pi minus 2.48 radians, which I plugged into a calculator, it indeed does give us negative 0.79. Now the question is, what time, t2, does the angle reach, 2 pi minus 2.48 radians, right? So imagine the thing starts out here, right? It reaches 2.4 radians at t1 is equal to 0.22 seconds. And if our intuition is correct and this plot gives us a clue, the time that it will reach this angle right here should be 0.35 seconds. And so I went ahead and plugged in 2 pi minus 2.48 radians, setting it equal to the argument in the cosine, right? So the argument in the cosine is an angle. It's 10 times a time plus 0.28 radians. This time it's t2. And so I just set the argument inside the cosine function equal to the angle that I'm interested in, which is 2 pi minus 2.48 radians. And so if you solve for t2 this time, you do indeed get 0.35 seconds. So indeed, this is how you would get the second time when the block reaches negative 0.20 meters. And then the third time, right, is just 0.22 right here plus a period. And one last thing I'd like to mention is just that to get the future times at x equals negative 0.20 meters, you just need to take the first time, which is 0.22, plus n, which is just an integer, times the period. So just for the odd numbers of, the odd times, it comes back, like 3, 5, and 7. The 5th and 7th and 9th time it comes back. You just have to keep adding multiples of this period. And then to get the even times, you just start at t2, and then again, just add multiple times of that period. So hopefully that made some sense. I hope it gave some insight as to how I kind of really reformulated this problem from a physics problem into a very mathematical one. And I hope it was interesting. Leave a comment below if you enjoyed seeing me explain my thought process. Leave a comment also if you have other ideas of how you would have solved it. And yeah, thank you for watching, and I will be back with more videos. Take it easy, everyone.